There's a moment just after the sun sets and the first stars appear when the sky stops feeling like a ceiling and starts feeling like a door to something vast, ancient, and utterly mysterious. Every pinprick of light up there isn't just a star. It's a question waiting to be answered, a riddle whispered across billions of years, and the craziest part: we've only begun to decipher them. Welcome to a journey that will take us to the very edge of what we know, where the universe stops giving easy answers and starts throwing curveballs that defy logic. Today, we're unraveling 27 cosmic puzzles, clues from the farthest reaches of space that leave even the sharpest scientists scratching their heads. Think about the last time you looked up and felt small under that endless expanse. Now imagine discovering something up there that shouldn't exist, a signal with no obvious source, a planet orbiting where no planet should be, or a flicker of light that behaves like nothing we've ever seen. These aren't just oddities, they're cracks in the foundation of our understanding, hints that the cosmos might be playing by rules we haven't even imagined yet. Some of these mysteries could rewrite textbooks, others might force us to ask entirely new questions about reality itself. And that's what makes this exploration so thrilling. Every clue we uncover doesn't just provide answers, it reshapes the very questions we're asking. So why does any of this matter to you? Because these puzzles aren't just for astronomers in lab coats. They're pieces of a story that belongs to all of us, a story about curiosity, perseverance, and the human drive to make sense of the unknown. Whether it's a bizarre radio signal repeating like a cosmic heartbeat or a galaxy spinning in the wrong direction, each of these 27 clues is a reminder that the universe is stranger, more wondrous, and more humbling than we ever dreamed. And by the end of this journey, you won't just see the night sky differently, you'll feel it differently too. So let's dive in. The cosmos is waiting, and its greatest mysteries are about to get a little less mysterious. Late one August night in 1977, as most of the world slept, a telescope in Ohio caught something that would haunt astronomers for decades. The Big Ear radio telescope, designed to scan the cosmos for whispers of intelligence beyond Earth, suddenly recorded a spike so powerful and peculiar that it stood out like a scream in silence. For 72 impossibly long seconds, this narrowband radio signal blazed across the frequency. Hydrogen naturally emits a frequency many scientists theorized aliens might use to get our attention. When researcher Jerry Amon saw the data printout days later, he circled the alphanumeric code representing the signal's intensity and scribbled a single word in the margin: "Wow." Here's what makes this cosmic shout so baffling. Unlike the random crackle of distant quasars or the predictable pulses of rotating neutron stars, the WOW signal was laser-focused in frequency and eerily silent before and after its brief appearance. It matched exactly what scientists predicted an intentional extraterrestrial transmission might look like, yet despite 47 years of searching that exact same patch of sky, we've never heard it again. Some argue it could have been a naturally occurring phenomenon we don't yet understand, like a comet's hidden radio emissions or an exotic stellar event. Others point out that no known celestial object behaves this way, and if it was aliens, why transmit just once? Why no follow-up? The more you examine this mystery, the stranger it gets. The signal originated near a star group called Chi Sagittarii, about 120 light-years away, close enough that a civilization there could have detected our first radio broadcasts around the same time we sent them. But here's the kicker: modern telescopes have scanned thousands of stars in that region and found no repeating signals, no megastructures, no technosignatures. Just silence. It's as if the universe handed us a single, perfect clue and then erased the crime scene. Maybe that's why this 72-second burst still captivates us. Not because it answered anything, but because it proved how much wonder is left to uncover. Every time we point a telescope at the stars, we're not just searching for answers, we're listening for the next cosmic whisper that might change everything. Picture a galaxy like our Milky Way, a vast spinning pinwheel of stars, planets, and cosmic dust. Now imagine this: if everything we can see in that galaxy were the only matter it contained, the entire structure should have torn itself apart billions of years ago. The outer stars rotate so fast that the gravity from visible matter couldn't possibly hold them in orbit, and yet somehow galaxies stay intact, the only explanation. Some invisible force must be anchoring them together, like the hidden roots of a tree keeping its branches from flying off in a storm. This is the essence of dark matter, the universe's best-kept secret, making up 85% of all matter yet refusing to show itself. For decades, scientists have chased shadows in the dark. We know dark matter exists because its gravitational grip bends light around galaxies in ways that can't be explained otherwise, an effect called gravitational lensing. It's like watching an invisible hand distort the view through a glass window. But here's where things get weird. Despite building detectors in abandoned mines, launching telescopes into orbit, and smashing particles together at near light speeds, we've never directly caught a single dark matter particle. Some theories suggest these particles are WIMP, weakly interacting massive particles, that barely interact with normal matter except through gravity. Others propose actions, hypothetical ultra-light particles that could flow through the cosmos like an intangible river. But what if we've been asking the wrong question entirely? A small but growing group of physicists argues that dark matter might not be matter at all. Instead, they think Einstein's theory of gravity, while brilliant, might need tweaking at the vast scales of galaxies. This idea, called modified Newtonian dynamics or MUND, suggests gravity behaves differently where accelerations are incredibly weak, like the outskirts of galaxies. It's a radical notion, like realizing the rules of chess change when the board gets too big. Yet even man can't explain all the observations, leaving us stuck between two unsettling possibilities. Either 85% of the universe is made of something we can't detect, or our understanding of gravity, the force we thought we knew best, is fundamentally incomplete. The hunt for answers has led to some of science's most daring experiments. In an old gold mine in South Dakota, the LUX Zeppelin detector waits in total darkness, its tank of liquid xenon poised to catch the faintest flash of a dark matter collision. Meanwhile, the European Space Agency's Euclid telescope maps the cosmos in 3 dimensions, tracing the invisible scaffolding of dark matter that shapes the universe. Every null result, every failed detection tightens the mystery, because here's the stunning truth: dark matter isn't just a missing piece of the puzzle. It's a mirror held up to our ignorance, revealing how much we still don't know about the fabric of reality. Whether it's particles or revised laws of physics, one thing's certain: solving this riddle won't just fill a gap in our textbooks. It'll rewrite them. Imagine a cosmic strobe light flashing so brightly it outshines 500 million suns, but only for a fraction of a second. That's the bizarre reality of fast radio bursts, some of the most energetic and fleeting signals in the universe. First discovered in 2007, these mysterious blips of radio waves travel billions of light years just to vanish almost as soon as they arrive. Some burst once and never repeat, like a firework exploding in the void. Others flicker on and off at random intervals, as if the cosmos itself can't decide whether to keep sending them. What could possibly generate such staggering energy in mere milliseconds? The leading suspect is a type of dead star called a magnetar, a neutron star with a magnetic field so intense it could erase a credit card from halfway across the solar system. In April 2020, astronomers got lucky when a magnetar in our own galaxy erupted with an FRB, finally linking these bursts to a tangible source. But here's the twist. While that outburst confirmed magnetars can produce FRBs, it didn't explain all of them. Some distant bursts are far more energetic than anything our local magnetar could muster, suggesting there might be multiple cosmic factories pumping out these signals. Then there's the repetition problem. Most FRBs flash once and disappear, but a handful, like the famous repeater in a dwarf galaxy 3 billion light-years away, keep coming back at irregular intervals. This unpredictability has fueled wilder theories, from colliding black holes to cosmic strings left over from the Big Bang. And yes, a few scientists have even dared to ask, could these be engineered signals? If an advanced civilization wanted to broadcast its presence across the universe, encoding information in millisecond bursts would be an efficient way to do it. The real challenge lies in catching these bursts in action. Since their discovery, telescopes like CHIME in Canada have turned the hunt into a cosmic game of whack-aim-mole, spotting dozens of FRBs monthly, yet solving their origin feels like trying to reconstruct a lightning bolt from its thunder. Each new detection adds another piece to the puzzle. Some bursts arrive polarized, their radio waves twisted like a corkscrew, hinting at extreme magnetic environments. Others come with lower frequency afterglows, as if the universe is leaving behind breadcrumbs. One thing's certain, FRBs aren't just cosmic static. They're messengers carrying clues about the spaces they've traveled through, the sparse gas between galaxies, the magnetic fields weaving through the cosmic web. Every burst is a time capsule holding secrets about the universe's structure and history. And while we're still years away from cracking their code, one truth remains. In a cosmos full of mysteries, fast radio bursts remind us that sometimes the loudest signals come from the quietest questions. Right now, as you watch this, our galaxy is falling. Not just floating or drifting, falling at over 2 million kilometers per hour towards something we can barely see. Astronomers call this the Great Attractor, a gravitational anomaly so powerful it's dragging the Milky Way and 500,000 other galaxies toward a point in space hidden behind the thick dust clouds of our own galaxy's core. It's like being in a boat caught in a river's current, but realizing too late there's a waterfall ahead, one we can't see because of the mist. For decades, this cosmic mystery resisted investigation simply because of its location. The Great Attractor sits in what astronomers call the zone of avoidance, a region of the sky obscured by the Milky Way's bulge, where stars and dust block our view of the distant universe. Early telescopes might as well have been staring into a cosmic blind spot, but thanks to infrared and radio instruments that peer through the dust, we've begun piecing together clues. What we've found is both enlightening and deeply unsettling. The leading theory suggests the attractor isn't a single monstrous object, but an enormous concentration of mass, likely a supercluster of galaxies weighing as much as 100,000 Milky Ways. Imagine a crowded city of galaxies, their combined gravity pulling everything nearby into their orbit. Yet even this explanation feels incomplete. The motion of galaxies near the attractor suggests there might be something even larger behind it, an unimaginably vast structure nicknamed the Shapley Attractor that could be pulling both the Great Attractor and us toward it. It's a cosmic matryoshka doll of gravity, each layer revealing a bigger, more mysterious force. But here's what keeps scientists up at night. What if the Great Attractor isn't just more of the same galaxies and dark matter, but something weirder? Some have floated the idea of a parallel brain, a higher dimensional gravity source leaking into our universe. Others wonder if it's a remnant of the Big Bang's unevenness, a kink in spacetime itself. Every new observation adds complexity. Recent studies found galaxies moving faster than the attractor's gravity should allow, hinting at forces we haven't accounted for. The quest to map this invisible maelstrom has driven some of astronomy's most ambitious projects. The Parkes Radio Telescope in Australia has spent years stitching together a galactic weather map, tracing hydrogen gas currents to infer the attractor's shape. Meanwhile, the European Space Agency's Gaia mission plots the precise motions of millions of stars, searching for gravitational fingerprints. Each dataset brings us closer to understanding why, in a universe that's supposed to be expanding evenly, we're caught in a silent, unstoppable tide. Perhaps the most humbling realization is this: the Great Attractor isn't just pulling us toward a place, it's pulling us toward a question. However we eventually explain it, whether as a cluster, a shadow of something grander, or a flaw in our gravity models, one truth remains. The universe doesn't just contain mysteries, it moves us toward them, literally and endlessly, reminding us that the map of the cosmos is still being drawn, with our galaxy swept along in its currents. In the constellation Cygnus, 1,400 light-years away, a star behaves like nothing else we've ever seen. Tabby's star, officially named KIC 8462852, doesn't just flicker, it plunges into darkness unpredictably, dimming by as much as 22% at times, as if something massive and jagged keeps passing in front of it. Imagine standing under a street lamp that doesn't just flicker but occasionally blacks out entirely, like a hand repeatedly covering the bulb. That's the level of strangeness we're dealing with here. When astronomer Tabetha Boyajian and her team first spotted this anomaly in data from the Kepler Space Telescope in 2015, the explanations ranged from plausible to downright sci-fi. A planet, impossible even a Jupiter-sized world, would only block about 1% of the star's light. A swarm of comets that could explain some dips, but not the sheer scale or irregularity. Then came the wild card hypothesis. Could this be evidence of alien megastructures like a Dyson swarm, a vast array of energy collecting satellites built by an advanced civilization? It's a tantalizing thought, but here's the catch. Extraordinary claims require extraordinary evidence, and Tabby's star has been stingy with answers. The plot thickened when astronomers dug into historical data. Old photographic plates revealed something startling. Tabby's star had been gradually dimming by about 14% over the past century. Stars don't just fade like that without a reason. Some suggested it might be consuming a planet, or perhaps surrounded by a colossal ring system tilted at just the right angle to create erratic shadows. Others pointed to interstellar debris, a cloud of dust and rubble from a catastrophic collision, drifting between us and the star. Then there's the timing. In 2017, the star's most dramatic dimming event lasted nearly a week, dropping its brightness in a way that looked almost intentional, as if someone kept adjusting a cosmic dimmer switch. Ground-based telescopes and amateur astronomers worldwide trained their lenses on Cygnus, hoping to catch the culprit in the act. Yet every observation raised more questions. Spectroscopic data ruled out some natural explanations like vast dust clouds because the dimming affected all wavelengths of light equally, something most cosmic debris doesn't do. Today, Tabby's star remains a riddle wrapped in a mystery. New instruments like the James Webb Space Telescope might finally crack the case, peering through dust or spotting chemical traces that hint at artificial structures. But here's the beautiful irony. Whether the answer turns out to be comets, debris, or something even more exotic, this star has already taught us how little we know about cosmic behavior. It's forced astronomers to rethink what's possible, to question assumptions, and to stay open to the idea that sometimes the universe's strangest signals aren't just noise, they're invitations to look deeper. And that's the real gift of Tabby's star. It's not just a puzzle to solve, it's a reminder that the cosmos always has another surprise up its sleeve. The universe keeps immaculate accounting, every proton, neutron, and electron accounted for since the beginning of time. Or so we thought. Here's the problem. When we tally up the lithium produced in the Big Bang, the numbers don't add up. According to our best models, that primordial fireball should have forged about 3 times more lithium than we actually detect scattered across stars and gas clouds today. It's as if the cosmos misplaced an entire elemental paycheck, and this discrepancy isn't just a clerical error. It threatens to unravel parts of our origin story. Why lithium? Because this lightweight metal, the same stuff powering your phone battery, acts like a cosmic receipt. In the first 20 minutes after the Big Bang, when the universe was a seething nuclear forge, protons and neutrons fused into hydrogen, helium, and trace amounts of lithium and beryllium. The ratios of these elements were locked in place as the cosmos cooled, becoming a fingerprint we can still measure in ancient stars. But when astronomers analyzed these stellar time capsules, the lithium came up short. Even accounting for stellar processes that destroy lithium over time, we're missing roughly 2/3 of the expected supply. So where did it go? One possibility is that stars are far more efficient lithium shredders than we realize. Young, turbulent stars might drag lithium down into their cores where nuclear reactions vaporize it, like a cosmic paper shredder hidden beneath a seemingly calm surface. Observations of certain star clusters support this. Stars with deeper convective zones show less lithium, as if they've been stirring it into oblivion. But here's the catch. Even if every star in the universe went on a lithium-destroying spree, simulations suggest it still wouldn't account for the staggering deficit. That's led physicists to consider wilder solutions. Could dark matter particles interact with lithium in ways we haven't imagined, effectively erasing it from the cosmic ledger? Or does lithium get trapped in unexpected places, like the diffuse gas between galaxies, too faint for our telescopes to spot? There's even a radical proposal that early universe physics didn't play out exactly as we've modeled. Maybe unknown particles or forces altered nuclear reaction rates in those first critical minutes, skewing the element ratios before stars even formed. The stakes are higher than they seem. Lithium isn't just missing, it's a litmus test for the entire Big Bang model. If we can't explain this gap, it might hint at gaps in our understanding of nucleosynthesis itself. That's why labs worldwide are racing to replicate those primordial conditions. Particle accelerators smash nuclei together at energies mimicking the infant universe, while space telescopes like the James Webb scan ancient stars for lithium traces frozen in time. What makes this mystery so compelling is its duality. On one hand, it's a forensic investigation into the universe's first moments. On the other, it's a reminder that even our most successful theories have unresolved edges, places where the cosmos winks at us, withholding answers until we ask better questions. Solving the lithium problem won't just fill a gap in our periodic table. It might reveal entirely new chapters in the story of how everything began. In the echoing silence between planets, where sunlight barely reaches and cosmic dust floats undisturbed, two of humanity's oldest robotic explorers were caught doing something impossible. Pioneer 10 and 11, launched in the early 1970s to study Jupiter and Saturn, kept drifting off course not by much, just enough to raise eyebrows. Over billions of kilometers, their trajectories deviated by roughly the width of a football field each year. A tiny error, but in the precise world of orbital mechanics, where gravitational calculations are accurate enough to fling probes across the solar system, even a whisper of unexplained motion is a shout for attention. At first, scientists suspected mundane explanations, perhaps a fuel leak or thruster misfire. But as decades of data piled up, the anomaly refused to vanish. The pioneers weren't just drifting, they were slowing down ever so slightly, as if space itself had a tiny bit more friction than expected. The effect was minuscule, about 10 billion times weaker than Earth's gravity, yet utterly persistent. By the late 1990s, the puzzle had a name, the Pioneer Anomaly, and it sparked a firestorm of speculation. Was this a flaw in our understanding of gravity? Evidence of dark matter's gravitational tug, or perhaps something even stranger, like a previously unknown long-range force acting on spacecraft? The most widely accepted solution emerged in 2011 when a team of researchers proposed an elegant culprit: heat. The pioneers, powered by radioactive plutonium, constantly radiated warmth from their electronics and power systems. That thermal energy, bouncing unevenly off the spacecraft's dish-shaped antennae, could have created a tiny but constant push, like a car idling with one brake slightly engaged. Computer models seem to confirm it, showing how uneven heat flow might explain most of the drift. Case closed, not quite. Skeptics point out lingering gaps. The heat theory accounts for about 85% of the anomaly, leaving a stubborn residue unexplained, and other spacecraft, like New Horizons, haven't shown the same drift despite similar designs. Some researchers wonder if the pioneers stumbled into a realm where our physics models need tweaking, like Newton's laws behaving differently at extremely low accelerations, an idea called modified inertia. Others speculate about interactions with the quantum vacuum, where particles flicker in and out of existence, potentially exerting subtle pressure. What makes the Pioneer anomaly so captivating isn't just the mystery itself, but what it represents. In science, the smallest inconsistencies often lead to the biggest breakthroughs. Mercury's wobbling orbit in the 19th century hinted at general relativity. The faint glow of cosmic microwave background radiation revealed the Big Bang's afterglow. The Pioneer's tiny deviation might not rewrite textbooks, but it's a humbling reminder. Even in the era of gravitational wave detectors and quantum computers, the universe still holds pockets of beautiful, stubborn uncertainty. Every unexplained drift, every faint anomaly is a breadcrumb trail leading to deeper questions, and perhaps one day deeper answers. The universe is unimaginably vast, with trillions of planets scattered across billions of galaxies, so many that statistically Earth shouldn't be special. Yet when we listen for alien voices or search for cosmic megastructures, all we hear is silence. This eerie contradiction is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" It's one of the most profound questions we've ever faced, forcing us to reckon with both the possibility of cosmic loneliness and the unsettling idea that advanced civilizations might be hiding from us, or worse, disappearing before they can say hello. Let's break down the numbers. Our Milky Way alone contains an estimated 100 billion stars, with at least 20 billion Earth-sized planets orbiting in habitable zones. Even if only 1 in a million of those worlds developed intelligent life, there should still be thousands of civilizations out there, some likely older and more advanced than ours by millions of years. So why haven't we seen a single radio signal, artifact, or engineering project spanning the stars? The theories attempting to explain this silence range from sobering to spine-chilling. One camp argues that intelligent life might be exceptionally rare, not just in space, but in time. Earth took 4.5 billion years to produce a species capable of broadcasting its existence. What if that window is astronomically narrow? Complex life might require such precise conditions: a stable star, plate tectonics, a large moon for tidal regulation, that most habitable planets never cross the finish line. Others suggest that technological civilizations inevitably hit a great filter, a catastrophic bottleneck that prevents long-term survival. This could be environmental collapse, runaway artificial intelligence, or nuclear war, an unsettling possibility given humanity's current trajectory. Then there's the zoo hypothesis. Imagine an interstellar protocol where advanced civilizations deliberately avoid contact, observing us like animals in a cosmic wildlife preserve until we reach some maturity threshold. It's a comforting thought, implying we're not alone, just quarantined, but darker variations exist. Some consider whether predators lurk in the galactic dark, forcing societies to stay quiet to avoid attracting attention. After all, history shows that when advanced cultures encounter less developed ones, the results are rarely peaceful. perhaps the most mind-bending explanation is that we're simply not looking the right way. Our radio telescopes scan for signals similar to our own, but what if aliens communicate via neutrinos, gravitational waves, or some medium we haven't discovered yet? Or maybe they've transcended biology altogether, existing as digital intelligences in supercomputers, leaving no trace we'd recognize as life. The universe is 13.8 billion years old, plenty of time for civilizations to rise, evolve beyond recognition, and vanish without a whisper. What makes the Fermi Paradox so compelling isn't just the lack of answers, it's how the question mirrors our own existential anxieties. Are we a fluke destined to fade without ever knowing neighbors, or are we on the cusp of discovering we're part of something vast and ancient? Every silent night sky is both a mystery and a mirror, reflecting back our deepest hopes and fears about what or who might be out there. And until we know for sure, the stars will keep their secrets, leaving us to wonder if the universe is playing hide and seek, or if we're the only ones left to play the game. Imagine mapping the afterglow of creation itself, the cosmic microwave background, a faint whisper of heat left over from the Big Bang. This ancient light, traveling for 13.8 billion years, should be perfectly uniform, a random scatter of hot and cold spots like static on an old television. But when scientists plotted this celestial fossil, they found something that sent chills down their spines. The universe has a preferred direction, an eerie alignment so bizarre they nicknamed it the axis of evil. Here's what makes this so unsettling. According to everything we know about cosmic inflation, the infant universe expanded so rapidly that no region should have been able to communicate with another. The CMB's temperature fluctuations should be like dice rolls, completely independent. Yet multiple studies, including data from the Planck satellite, show hot and cold spots aligning along a specific axis like beads on a string. It's as if someone drew an arrow across the cosmos, pointing from the constellation Leo toward Aquarius, a cosmic up and down that defies the principle of isotropy, the idea that the universe looks the same in all directions. Could this just be a fluke? The odds are astronomically low, about 1 in 10,000, but not impossible. Some researchers argue we're seeing a statistical ghost, a quirk of how we process the data. Others suggest subtler explanations, like our solar system's motion, distorting measurements, or interstellar dust casting shadows we don't fully understand. But the wildest theories go much further. What if this axis is a fossil imprint of whatever existed before the Big Bang? Some models of cyclic universes propose that a previous cosmic epoch left behind gravitational scars, warping the newborn universe like fingerprints pressed into clay. Then there's the multiverse angle. If our universe is one bubble in an infinite foam of others, its shape might bear marks of neighboring realms tugging at its edges in those first fractions of a second. The axis could be a collision scar, like a dent in a car fender from a long-forgotten crash. Even quantum gravity gets a seat at the table. Some formulations suggest space-time itself might have a preferred quantum geometry, like the grain in a piece of wood, leaving subtle directional biases in the CMB. But here's the twist: the axis of evil isn't just a scientific puzzle. It's a philosophical grenade. If the universe does have a preferred direction, it undermines the Copernican principle, the bedrock idea that Earth, and by extension humanity, holds no special place in the cosmos. Suddenly, we're back to grappling with the uncomfortable question: are we, in some strange way, aligned with the universe's fundamental structure? Future telescopes may settle the debate. Projects like the Simons Observatory in Chile aim to map the CMB with unprecedented precision, hunting for secondary patterns that could confirm or crush these theories. Until then, the axis remains one of cosmology's most tantalizing loose threads, a reminder that even our best models of reality might be missing something profound. Whether it's a measurement artifact or a crack in the foundation of modern physics, one thing's certain: the universe loves keeping us humble. Just when we think we've mapped the heavens, it whispers, "Look again." Black holes don't just swallow matter, they devour information. Toss a book into one, and according to Einstein's general relativity, every word, every ink molecule gets crushed beyond recovery at the singularity. But quantum mechanics insists information can't be destroyed, only scrambled. This irreconcilable clash birthed the black hole information paradox, a cosmic tug of war between our two most successful theories of reality. For decades, physicists assumed Hawking radiation, the faint glow black holes emit, carried no data about what fell in. That changed in 2019 when a team calculated that quantum entanglement might encode swallowed secrets in this escaping heat, like invisible ink revealing itself under the right light. So how could information possibly escape a black hole's grip? The answer might lie in holography, the radical idea that all 3D events inside a black hole are encoded on its 2D surface, like a cosmic DVD storing three-dimensional movies on a flat disk. When matter crosses the event horizon, its information gets smeared across this boundary like fingerprints on glass. Later, as Hawking radiation trickles out, it peels those fingerprints away, carrying them into the universe. It's as if black holes aren't cosmic shredders, but the universe's most secure hard drives, destroying nothing, just encrypting everything, but skeptics aren't convinced. If information escapes, where's the mechanism? Some argue the radiation process would require a firewall of ultra-high energy particles at the event horizon, incinerating anything trying to cross, a notion that violates relativity's prediction of an uneventful plunge. Others propose less violent solutions, like quantum Hare's subtle disturbances on the black hole's surface that imprint data onto outgoing radiation. The debate grew so heated that in 2016, Stephen Hawking himself revised his stance, suggesting black holes might have soft hair, low-energy quantum fields that preserve information without cataclysmic fireworks. The stakes here are astronomical. If information truly vanishes, quantum theory needs rewriting. If it escapes, general relativity might need patching. And if neither theory bends, we could be staring at the first cracks in our understanding of spacetime itself. Recent lab experiments simulating black holes with supercooled atoms and lasers offer tantalizing clues, showing information can survive conditions once thought obliterating. Meanwhile, gravitational wave detectors listen for echoes in black hole collisions, potential whispers of preserved data. What makes this paradox so captivating isn't just the physics, it's the philosophy. At its core, this is a debate about whether reality keeps receipts. If black holes erase information, the universe has an escape clause from its own accounting. But if every atom's history survives, even in scrambled form, then nothing, not even the void's embrace, truly lets us forget. Until we solve this riddle, black holes will remain more than cosmic oddities. They're the ultimate test of whether the universe plays by rules we can ever fully grasp. In the sprawling cosmic web where galaxies cluster like cities linked by highways, there's a place so empty it feels like the universe forgot to fill in a blank. The Boötes void, a staggering spherical region spanning 330 million light-years, contains scarcely 60 galaxies where there should be thousands. To put that in perspective, if the Milky Way were a single grain of sand, the Boötes void would be a hollow sphere the size of a football stadium with just a handful of grains scattered inside. It's not just a gap. It's a cosmic desert so vast and barren that light crossing it would take hundreds of millions of years without encountering anything but the occasional dim galactic oasis. How does something this empty even exist? Current models of galaxy formation suggest the universe's structure arose from tiny density fluctuations in the primordial plasma, like ripples frozen in time during the Big Bang. Gravity amplified those ripples, pulling matter into filaments and knots we now see as galaxy clusters. But the Boötes void defies this logic. It's too big, too smooth, too perfectly empty. Statistically, such a void shouldn't exist in our observed universe. It's like finding a mile-wide bubble in a pot of boiling water. Nature doesn't usually leave holes that large untouched. This anomaly has sparked theories that sound more like sci-fi than astrophysics. One provocative idea suggests the void might be the imprint of a collision with a parallel universe, a bubble from another cosmic inflation event brushing against ours and pushing matter away like repelling magnets. Others propose it could be evidence of an ancient, ultra-massive black hole that devoured everything in its vicinity before vanishing, but the most unsettling possibility. That the Boötes void isn't an accident at all, but a signature of something far stranger, a flaw in our understanding of dark energy's role in shaping the cosmos. Here's why this matters beyond curiosity. Voids aren't just empty space, they're active players in cosmic evolution. Their gravitational pull tugs on surrounding galaxies, influencing the large-scale flow of matter. The Boötes void's extreme nature challenges our assumptions about how much push dark energy exerts and whether its strength has changed over time. If voids like this are more common than we thought, it could mean our universe's expansion isn't just accelerating, it's doing so unevenly, like a balloon inflating faster in some patches than others. Efforts to solve this puzzle have led astronomers to map the void's few galaxies in exquisite detail, searching for patterns in their distribution or motion that might hint at its origin. Meanwhile, simulations try, and often fail, to recreate such a perfect emptiness under known physics. The Boötes void stands as a humbling reminder. Sometimes the most profound cosmic mysteries aren't about what's there, but what isn't. In the grand tapestry of the universe, absence speaks as loudly as presence. And this great nothing might hold clues to everything we don't yet understand about the structure of reality itself. Perhaps the most poetic lesson here is how emptiness can unsettle us. We expect the cosmos to be full, vibrant, bustling, not scarred by voids so vast they defy comprehension. Yet it's precisely these gaps that challenge us to look deeper, to question not just what we see, but what we don't. The Boötes void isn't just a cosmic oddity. It's an invitation to wonder what else might be missing from our maps and whether, in those blank spaces, the universe is hiding its most extraordinary secrets. The Moon today is a silent, airless world with no global magnetic field, just scattered remnants of ancient magnetism frozen into its rocks. But 4 billion years ago, something extraordinary happened. Apollo mission samples revealed that this seemingly inert orb once crackled with a magnetic field up to 100 times stronger than Earth's does now. That discovery sent shockwaves through planetary science because, by all rights, the Moon's core is far too small and cool to have powered such a dynamo. It's like finding a dead flashlight that somehow once outshone a lighthouse, and nobody can figure out where the batteries were hidden. To understand why this is so baffling, picture Earth's magnetic field like an invisible force field generated by churning molten iron in our planet's outer core. This geodynamo requires 3 key ingredients: a liquid conductive layer, rapid rotation, and vigorous convection. The Moon fails on all fronts. Its core is only about 350 kilometers wide, barely 20% of its diameter, and likely cooled too quickly to sustain the necessary heat flow. Worse, the Moon spins sluggishly, completing just 1 rotation every 27 days. That's like expecting a wind turbine to power a city when it only turns once a month. Yet the evidence is undeniable. Lunar rocks dating back 3 billion to 4 billion years bear magnetic imprints proving they cooled in the presence of a robust field. So how did the lunar dynamo defy physics? One leading theory points to a cosmic tug-of-war. Early in its history, the Moon orbited much closer to Earth, and our planet's gravity may have stirred its core like a spoon swirling molten chocolate. Computer simulations show this mechanical stirring could have jump-started convection, generating a temporary magnetic field until the moon drifted farther away and the effect faded. Another proposal suggests the moon's mantle wasn't always the solid shell we see today. If it contained dense, radioactive elements like uranium and thorium, their decay could have superheated the core, fueling convection like a nuclear furnace. But the most tantalizing clue came in 2017 when researchers studying Apollo samples noticed something peculiar. The rock's magnetic signatures didn't just weaken over time, they flickered as if the dynamo kept turning on and off like a faulty generator. This has led to a radical idea. Perhaps the lunar field wasn't powered from within at all. Giant asteroid impacts during the moon's violent early years could have smashed its crust with such force that the shockwaves temporarily liquefied parts of the core, creating short-lived magnetic bursts. Imagine hitting a gong so hard that the vibrations briefly light up a bulb. That's the scale of energy we're talking about. Solving this mystery isn't just academic. Planetary magnetic fields act as shields, deflecting deadly solar radiation and preserving atmospheres. If small, rocky worlds like the moon can generate strong fields through unconventional means, it expands the possibilities for habitable exoplanets we've previously written off. Future missions like NASA's lunar vertex, set to land on the moon's Rayner Gamma magnetic anomaly in 2024, aim to map these fossil fields in unprecedented detail. Every new reading could rewrite our understanding of how celestial bodies protect themselves and, by extension, how life might find shelter across the cosmos. The moon's magnetic past is more than a lunar quirk. It's a masterclass in cosmic humility, reminding us that even our closest neighbor still guards secrets capable of upending textbook wisdom. Whether powered by tidal forces, radioactive decay, or celestial collisions, one thing's clear: a world we thought we knew has been quietly keeping a dynamo's worth of surprises. And somewhere in those ancient rocks lies the answer to a question we're only beginning to ask: how many other impossible magnetic fields are waiting to be discovered? Picture two groups of scientists measuring the same mountain, one using footsteps, the other with laser beams. Both methods are proven precise, and yet somehow they keep arriving at different heights. That's essentially the crisis cosmologists face with the Hubble tension, a stubborn discrepancy in measuring how fast the universe is expanding. One approach, relying on the cosmic microwave background, the afterglow of the Big Bang, suggests an expansion rate of about 67 kilometers per second per megaparsec. But when astronomers use pulsating stars called Cepheids or exploding supernova as cosmic yardsticks, the number jumps to 73. That 6-kilometer gap might sound trivial, but in the high-stakes world of precision cosmology, it's a chasm wide enough to swallow our current understanding of physics. Why does this mismatch matter? Because the expansion rate, known as the Hubble constant, is the universe's speedometer. It tells us not just how fast space is stretching, but also how old the cosmos is, what it's made of, and where it's headed. For decades, we assumed this number was consistent, governed by dark energy's steady push. But the tension suggests two terrifying possibilities. Either we've made a colossal measurement error, or dark energy isn't the constant force we thought it was. Imagine driving a car where the speedometer keeps resetting itself suddenly. Every exit you plan to take might be in the wrong place. The plot thickens when you examine the methods. The CMB approach, championed by the Planck satellite, works backward from the infant universe's snapshot, assuming standard physics held true for 13.8 billion years. Meanwhile, the local ladder, measurements using Cepheids and supernova as mile markers, paint a picture of today's expansion. If both can't agree, something might have tweaked the universe's gears along the way. Some theorists propose dark energy could be evolving, growing stronger or weaker over time like a battery losing its charge. Others wonder if exotic particles, like early dark energy, briefly surge during cosmic dawn, leaving invisible fingerprints on the expansion rate. Then there's the nuclear option. Maybe our entire framework needs an overhaul. The standard model of cosmology, dubbed Lambda CDM, has been astronomy's North Star for years. But what if dark matter interacts with itself in ways we haven't accounted for? Or gravity behaves differently on cosmic scales? Even wilder ideas float around, like the universe being lumpier than we thought, with dense regions pulling measurements askew like funhouse mirrors. Every proposed fix feels like trying to balance a wobbly table by cutting one leg shorter, solve one problem, and three more pop up, the most fascinating part. This isn't just academic squabbling. New telescopes are wading into the fray. The James Webb Space Telescope's razor-sharp infrared eyes are double-checking Cepheid distances, while next-generation CMB experiments like Simon's Observatory hunt for anomalies in the ancient light. If the tension holds, we might be staring at the next Copernican revolution, a moment where the universe forces us to admit we've been missing something fundamental all along. Until then, the Hubble tension remains cosmology's most tantalizing unsolved equation, a reminder that even our best models are just sketches waiting for the universe to fill in the details. On October 19, 2017, astronomer Robert Warwick made a discovery that would send shockwaves through the scientific community. While reviewing images from the Pan-STARRS telescope in Hawaii, he spotted a faint dot moving at blistering speed, not along the gentle arc typical of solar system objects, but on a trajectory so steep it could only mean one thing. This visitor came from beyond our cosmic neighborhood. By the time telescopes swung into action, the object dubbed Oumuamua, Hawaiian for scout, was already racing away at nearly 95,000 kilometers per hour. But its exit would prove even stranger than its arrival, leaving behind a mystery that still divides astronomers today. First, the basics. Oumuamua wasn't just our first confirmed interstellar visitor. It broke every rule in the book. Most comets or asteroids follow predictable paths shaped by the sun's gravity. Yet this traveler accelerated slightly as it departed, as if pushed by an unseen force. Then there was its shape. Estimates suggested an elongated cigar or pancake, stretching perhaps 200 meters long but only 20 wide, a ratio more extreme than any natural object we've seen in our solar system. Even its reflectivity was bizarre, gleaming 10 times brighter than typical cometary ice. For an object that spent eons drifting between stars, it showed no signs of cosmic weathering, no dusty coma, no tail. It was as if the universe had tossed us a riddle wrapped in an enigma and sealed it with a wink. Explanations range from plausible to downright provocative. The acceleration could have come from outgassing sunlight vaporizing frozen gases beneath Oumuamua's surface, acting like tiny thrusters. But here's the catch: no gas was detected, which rules out most conventional comets. In 2020, researchers proposed it might be a chunk of solid hydrogen ice, a rarity that would explain both the acceleration and lack of visible outgassing. Yet hydrogen icebergs would evaporate quickly in interstellar space, making their survival unlikely. Another camp suggests nitrogen ice, similar to Pluto's glaciers, but again, the numbers don't quite add up. Then there's the hypothesis that sparked global fascination. Could Oumuamua be artificial? Harvard astronomer Avi Loeb famously argued its properties: the unusual shape, unexpected acceleration, and extreme reflectivity aligned suspiciously well with a light sail, a theoretical spacecraft propelled by solar radiation. While most scientists remain skeptical, the idea forces us to confront an uncomfortable truth. If an alien probe did pass through our solar system, we'd likely interpret it as just another weird rock. Our instruments aren't designed to detect extraterrestrial technology, only natural phenomena we already understand. What makes Oumuamua so haunting isn't just the unanswered questions. It's the realization that interstellar visitors might be more common than we thought, and we're woefully unprepared to study them. Since 2017, at least 2 more potential interlopers have been spotted, including the comet Borisov in 2019. Future telescopes like the Vera Rubin Observatory promise to catch others, perhaps even before they swing past the Sun. But Oumuamua remains the one that got away, a fleeting glimpse of something utterly foreign, challenging our assumptions about what lurks in the vast dark between stars. Perhaps the most profound lesson isn't about Oumuamua itself, but how we respond to cosmic surprises. When faced with the unfamiliar, science typically defaults to known explanations: icebergs, asteroids, measurement errors. Yet sometimes the universe sends us a curveball so strange it demands we widen the net of possibility. Whether Oumuamua was a nitrogen fragment, a hydrogen snowball, or something beyond our current imagination, its legacy endures as a reminder: the cosmos doesn't owe us easy answers. It only offers fleeting chances to ask better questions, and in that brief window before it vanished into the void, Oumuamua asked plenty. In the cosmic rulebook, dark matter is supposed to be the universal glue, the invisible scaffolding holding galaxies together. Every spiral, every elliptical, every dwarf galaxy we've studied leans on this mysterious substance to explain its structure and motion. Then along came NGC 1052DF2, a galaxy so defiant it tossed the rulebook out the cosmic window. Discovered in 2018, this faint, ghostly galaxy 365 million light-years away did the unthinkable. It appeared to have no dark matter at all. Not a trace. Its stars moved sluggishly, as if gravity itself had taken the day off, leaving astronomers staring at their screens in disbelief. At first, scientists assumed their measurements were wrong. After all, dark matter isn't just a component of galaxies, it's 85% of their mass. Take it away, and stars should fly apart like a merry-go-round spinning too fast. Yet DF2's stars orbited sedately, their speeds perfectly explained by the visible matter alone. Follow-up observations only deepened the mystery. The galaxy lacked the dense central bulge or spiral arms of typical galaxies, resembling instead a translucent jellyfish adrift in space. Even its globular clusters, tight knots of ancient stars, moved at a leisurely pace, showing no signs of dark matter's gravitational grip. The implications are seismic. If DF2 is real, not some measurement fluke or cosmic illusion, it challenges the very foundation of modern cosmology. One camp argues it's a freak accident, a galaxy stripped of its dark matter by a violent encounter. Picture 2 galaxies colliding, their dark matter halos slingshotting into space while the visible stars, like stubborn passengers, remained behind. Simulations show this can happen, but the odds are vanishingly slim. Others propose DF2 might be a failed galaxy, born from gas so unusually dense it never needed dark matter to condense into stars. But here's where things get radical. A small but vocal group of researchers sees DF2 as evidence for an alternative theory of gravity, modified Newtonian dynamics, or MUND. If gravity behaves differently at low accelerations, as MUND suggests, then dark matter might be an illusion, a mathematical band-aid for a flawed equation. DF2's serene stellar motions fit MUND predictions eerily well. Skeptics counter that most galaxies do require dark matter to make sense, leaving MUND to explain away anomalies piecemeal. The debate rages on, fueled by the discovery of a handful of other dark matter-deficient galaxies. Each one is a cosmic provocateur, forcing us to confront uncomfortable questions. Are these outliers proof of nature's creativity, or clues that our theories need rewriting? Future telescopes like the Vera Rubin Observatory will scan millions of galaxies, hunting for more rebels like DF2. Their verdict could reshape our understanding of gravity, dark matter, and the cosmic web itself. What makes DF2 so electrifying isn't just its defiance, it's the reminder that nature loves exceptions. Every time we think we've pinned down the rules, the universe tosses us a curveball. Whether this galaxy is a statistical oddity or a paradigm-shifting clue, it proves one thing: the cosmos still has cards up its sleeve, and we're only beginning to see the hand it's playing. When astronomers first mapped the cosmic microwave background, the faint afterglow of the Big Bang, they expected a fairly uniform tapestry of temperature variations. Tiny fluctuations, yes, but nothing too dramatic. Then they found the cold spot. Nestled in the constellation Eridanus, this eerily frigid region spans nearly 200 million light-years, chilling the surrounding space by about 70 microkelvin, a whisper in cosmic terms, but a scream in the precision world of cosmology. What makes it so unsettling isn't just its temperature. It's the growing realization that this might not be a random quirk of the early universe. It could be a bruise, evidence of a collision with another universe beyond our own. The simplest explanation is a supervoid, an enormous, underdense region of space where matter is unusually sparse. In such a void, photons from the CMB would lose energy as they traverse the expanding space, creating a cold imprint. But here's the catch: the cold spot is too cold, too large. Simulations show that even the most extreme void shouldn't produce a chill this profound. When researchers scanned the region with telescopes, they found galaxies, but nowhere near enough to explain the temperature drop. It's like opening an empty freezer and feeling a blast of Arctic air, then realizing there's no ice, just empty shelves radiating cold from nowhere. That's where things get speculative and thrilling. Some theorists propose the cold spot might be the imprint of a cosmic collision. In certain multiverse models, our universe isn't alone. It's one bubble in an infinite foam of others, each with its own physics, its own Big Bang. If another universe brushed against ours in the distant past, the energy exchange could have left a scar, a patch of space-time stretched thin, cooling the CMB like a cosmic draft from an open window. The idea sounds like science fiction, but the math holds up. Quantum fluctuations during inflation could have spawned these bubble universes, and their collisions would leave measurable fingerprints. The cold spot fits that fingerprint disturbingly well. Of course, not everyone's convinced. Critics argue that statistical anomalies happen, that in a universe as vast as ours, even the unlikeliest fluctuations can occur by chance. Others suggest more mundane explanations, like instrumental noise or foreground dust skewing the measurements, but the cold spot refuses to fade into the background. New data from the Atacama Cosmology Telescope and the Planck satellite only sharpens the mystery, ruling out some alternatives while leaving the door cracked for multiverse theories. What makes this icy enigma so captivating isn't just the science, it's the philosophical weight. If the cold spot is proof of a multiverse, it would be the first tangible evidence that reality extends beyond our cosmic horizon. We'd no longer be asking what's in our universe, but which universe are we in? Future telescopes, like the Simons Observatory, aim to scrutinize the cold spot's polarization patterns, hunting for telltale swirls that could betray a collision's shockwaves. Until then, this frigid anomaly remains cosmology's most tantalizing Rorschach test, a blank canvas where some see a void, others a window, and everyone, perhaps, a reflection of their own cosmic curiosity. The coldest places, it seems, ignite the hottest debates. There's a rule in physics so fundamental we rarely even think to question it: everything is made of particles. Electrons, quarks, photons, they're the cosmic Lego bricks assembling reality as we know it. But what if there's a hidden sector of the universe where this rule doesn't apply? Enter the unparticle hypothesis, one of the most delightfully bizarre ideas to emerge from theoretical physics in decades, proposed in 2007 by Harvard physicist Howard Georgi. it suggests the existence of a shadowy form of matter that doesn't behave like particles at all. Instead, it manifests as a strange, scale-invariant substance with no fixed mass or energy, more like a cosmic fog than a collection of discrete objects. The math behind unparticles is as elegant as it is mind-bending. Imagine a substance that doesn't follow the usual energy-mass relationship we see in particles. When you probe it, it doesn't resolve into individual bits, but instead acts like a continuous, rippling field with fractal properties. It's matter without particulate structure, like trying to grab hold of smoke only to watch it slip through your fingers in patterns that change depending on how tightly you try to grasp it. This isn't just an academic curiosity. Unparticles could solve some of cosmology's biggest headaches. Take dark matter. If it's made of unparticles, their unique, non-particulate nature might explain why our detectors have come up empty after decades of searching. They wouldn't interact via the usual channels, slipping past our experiments like ghosts through walls. But the implications go even deeper. Unparticles could be the key to other cosmic mysteries, like the inexplicable forces shaping galaxy rotation or the anomalous heat signatures in certain galaxy clusters. If this hidden sector exists, it might interact with our familiar particles through feeble, almost imperceptible forces, tugging at the fabric of reality in ways we're only beginning to model. Some theorists speculate that unparticle fields could even influence the behavior of neutrinos, those elusive subatomic particles that oscillate between flavors as they travel. The possibilities spiral outward, each more tantalizing than the last. Of course, not everyone's convinced. Critics argue that without direct experimental evidence, unparticle physics risks drifting into pure speculation. After all, how do you detect something that defies the very definition of detection? But here's the twist: we might already be sitting on clues. Certain anomalies in high-energy particle collisions, unexpected energy distributions, or rare decay pathways could hint at unparticle mediation. Even the faintest deviations from predictions at facilities like CERN might be cosmic breadcrumbs leading us toward this radical reimagining of matter. What makes the unparticle hypothesis so thrilling isn't just its potential to rewrite the rules, it's the audacity of the question itself. For centuries, we've assumed that to understand the universe, we must break it down into smaller and smaller pieces. But what if some things can't be broken down? What if the universe hides realms where the very concept of particle ceases to have meaning? Whether unparticles prove real or remain a beautiful mathematical phantom, they remind us that reality might be far weirder and more wonderful than our textbooks dare to suggest. And in that possibility lies the true magic of cosmic exploration, not just solving puzzles, but discovering entirely new kinds of questions. Beyond the orbit of Neptune, where sunlight dwindles to a faint glow and temperatures plunge near absolute zero, the Kuiper belt stretches like a frozen junkyard of cosmic leftovers. This icy realm, home to dwarf planets like Pluto and Eris, should theoretically extend smoothly for billions of kilometers, its population of frozen objects gradually thinning as we move outward. But around 50 astronomical units from the Sun, roughly 7.5 billion kilometers, something bizarre happens. The Kuiper belt doesn't fade away. It plummets like a cliff's edge dropping into an abyss. The number of detectable objects crashes to nearly zero. This sudden vanishing act, known as the Kuiper cliff, is one of our solar system's greatest unsolved riddles, and the leading theories to explain it range from a hidden ninth planet to celestial carnage on an unimaginable scale. Let's unpack why this drop-off is so perplexing. In the grand scheme of planetary formation, the outer solar system should be a gentle slope of debris, with icy bodies distributed relatively evenly beyond Neptune. Instead, it's as if someone built a fence at the 50-year mark, preventing anything substantial from existing beyond it. Early surveys, like those conducted by the Canada-France Hawaii telescope in the early 2000s, revealed this stark boundary. Later observations by pan-stars and other instruments confirmed it. The Kuiper belt doesn't just end, it stops abruptly and inexplicably. One compelling explanation involves gravity's invisible hand. Just as Neptune's pull sculpts the inner edge of the Kuiper belt, an unseen, massive object, often dubbed Planet 9, might be shepherding the outer edge. Simulations show that a distant planet, perhaps 5 to 10 times Earth's mass, could gravitationally eject or warp the orbits of smaller objects beyond 50°, creating the observed cliff. The math works, but there's a catch. Despite years of searching, no such planet has been found. Telescopes like Subaru and Vera Rubin continue scanning the outer dark, but until we spot this hypothetical world, the theory remains tantalizingly unproven. Then there's the cataclysmic alternative. Imagine our young solar system as a violent neighborhood, where nascent planets jockeyed for position before settling into their current orbits. During this chaotic epoch, a close encounter with a passing star or even a rogue planet might have ripped away the outer Kuiper belt, hurling its material into interstellar space. Astronomers call this stellar flyby scenario, and while it sounds dramatic, it's not without precedent. Studies of other star systems show such gravitational theft isn't just possible, it might be common. The Gaia spacecraft's precise mapping of stellar motions has even identified candidate stars that could have brushed past us billions of years ago, though proving their role in the cliff's formation remains speculative. Here's where things get truly strange. Some researchers argue the Kuiper cliff might not be a true edge at all, but an observational illusion. Beyond 50°, objects could grow so dark and diffuse that our current telescopes simply miss them. Alternatively, these distant bodies might cluster in orbits that rarely bring them into view, like needles hiding in a cosmic haystack. New missions like NASA's proposed Interstellar probe could settle the debate by venturing beyond the cliff to see what's really out there. Until then, the cliff stands as both a boundary and a beacon, a reminder that even in our own cosmic backyard, the universe keeps secrets waiting to be uncovered. What makes this mystery so thrilling isn't just the unknown, it's the stakes. Solving the Kuiper cliff could rewrite our solar system's history, revealing lost siblings, violent encounters, or entire classes of objects we've overlooked. Whether the answer lies in a hidden world, a celestial thief, or something even stranger, one truth remains: the edge of our known solar system isn't an ending. It's a question mark dangling in the dark, daring us to look further. The universe has a way of humbling even our boldest theories, and nothing proves this like the James Webb Space Telescope's latest discoveries. When JWST turned its infrared gaze toward the deepest reaches of space and thus the earliest moments of time, it captured something that shouldn't exist. Galaxies so massive, so structured, and so old that they defy every current model of cosmic evolution. These colossal star cities, spotted as they appeared just 300 million years after the Big Bang, weigh up to 100 billion times the mass of our Sun. To put that in perspective, that's like finding a fully grown redwood tree sprouting from a seed planted yesterday. The shockwaves from this revelation are still rippling through cosmology, forcing scientists to ask, did galaxies form in a way we've never imagined, or is our entire timeline of the universe's infancy catastrophically wrong? Let's unpack why these galaxies are so baffling. According to the standard model of cosmology, the early universe was a dark, primordial soup, a seething plasma too hot for atoms to form, let alone stars. Only after the cosmic microwave background was released around 380,000 years after the Big Bang could matter begin clumping together under gravity's pull. Simulations suggest the first protogalaxies should have been tiny, fragile things, taking hundreds of millions of years to merge into the spirals and ellipticals we recognize today. But JWST images tell a different story. These early giants aren't just large, they're mature, with intricate structures like disks and bulges that typically require multiple generations of stellar birth and death to sculpt. It's as if we opened a textbook to the first chapter and found a spoiler for the ending scrawled in the margins. The implications are staggering. If galaxies grew this fast, either our understanding of dark matter's role in seeding cosmic structures is incomplete, or star formation in the early universe operated under rules far more efficient than anything we've observed locally. Some theorists propose that the first stars might have formed differently, collapsing directly from primordial gas into behemoths hundreds of times the Sun's mass, burning bright and dying young in explosions that seeded subsequent generations with heavy elements at breakneck speed. Others wonder if dark matter itself behaved differently in those early epochs, clumping faster and more densely than current models allow. But the most radical possibility is that we've misjudged the universe's age entirely. Could the Big Bang have happened earlier than we think? It's a fringe idea, but a handful of researchers point to anomalies in the cosmic microwave background that might hint at a pre-Big Bang phase. Alternatively, what if time itself flowed differently in the early cosmos? Certain quantum gravity models suggest the speed of light, and thus the rate of causality might have been higher in the universe's infancy, effectively allowing structures to form in what appears to us as an impossibly short window. Amid the turmoil, one thing's certain: JWST has handed us a cosmic detective story with no easy answers. Every proposed solution raises new questions. If early stars were more efficient, why did that efficiency vanish? If dark matter clumped differently, what shut off that behavior? The telescope's next round of observations will target even earlier galaxies, hunting for patterns that might reveal whether these giants were cosmic one-offs or the tip of an iceberg. Meanwhile, theorists are racing to revise models, knowing that whichever explanation wins, it won't just tweak our understanding of galaxies, it'll redefine how we see the universe's first breaths. What makes this puzzle so exhilarating isn't just the science. It's the reminder that discovery doesn't always mean finding what we expect. Sometimes it means stumbling upon the impossible and realizing the universe has been waiting all along for us to catch up. Whether the answer lies in rewritten physics, overlooked forces, or something beyond our current imagination, one truth remains: the cosmos is far stranger and far more inventive than we ever dared to assume. And that's the real gift of these impossible galaxies, not just the questions they answer, but the ones they force us to ask. Most of the universe looks like a bustling city, galaxies clustered together in glowing knots, connected by filaments of gas and dust. But in the direction of the constellation Eridanus, there's a place where the cosmic metropolis gives way to an unsettling emptiness. The Eridanus supervoid isn't just a gap in space. It's a staggering spherical void nearly 1 billion light-years wide, so vast that if you stood at its center, you wouldn't see a single galaxy in any direction for hundreds of millions of light-years. And this isn't just empty space. It's a lack of space, a region where the universe itself seems to have skipped a beat. What makes this void so extraordinary isn't just its size, it's the way it warps our view of cosmic history. According to standard models, voids this colossal simply shouldn't exist. The early universe's quantum fluctuations, stretched by inflation, created a web of density variations that seeded galaxy formation. But statistical simulations show that a void this large and pristine would require a fluke so unlikely. It's like rolling a die 1,000,000 times and getting nothing but sixes. Even stranger, the Eridanus supervoid lines up almost perfectly with the CMB Cold Spot, that mysterious frigid patch in the cosmic microwave background we explored earlier. Coincidence? Unlikely. The leading theory suggests the void's immense emptiness acts like a cosmic downhill slope. Photons from the CMB lose energy as they traverse this underdense region, stretching their wavelengths and cooling the light we observe, just like a marathon runner slowing down as they climb out of a valley. But here's the catch, the math doesn't quite add up. While the supervoid can explain some of the cold spot's chill, the temperature drop is too extreme for even a void this size. That discrepancy has fueled wilder ideas. Could this be evidence of a bubble universe collision, where another cosmos brushed against ours in the distant past, leaving behind a scar in the form of this void? Or does the supervoid hint at exotic physics, dark energy behaving differently in these desolate regions, or even an ancient phase transition in the early universe that left behind a defect in space-time? The Eridanus supervoid forces us to confront a humbling truth. Our maps of the cosmos might be missing entire chapters. For decades, cosmologists assumed the universe's large-scale structure was roughly uniform, a cosmic foam where voids and filaments balanced out. But this billion-light-year blank spot suggests otherwise. It's as if we've been studying Earth's geography by only mapping the continents, oblivious to the Pacific Ocean's existence until someone finally looked west and gasped at the endless blue. Future sky surveys, like the Legacy Survey of Space and Time at the Vera Rubin Observatory, will scan millions of galaxies to hunt for other supervoids. If more of these cosmic deserts exist, they might rewrite our understanding of how structure evolves across the universe. Until then, the Eridanus supervoid remains a silent enigma, a reminder that sometimes the most profound mysteries aren't about what's out there, but what isn't. In the grand tapestry of existence, even emptiness speaks volumes. Picture the universe as a vast ocean, with galaxies adrift in its currents. Now imagine spotting something impossible: hundreds of galaxy clusters, all streaming in the same direction at breakneck speeds, as if pulled by an invisible tide. This isn't science fiction, it's the dark flow, one of cosmology's most unsettling discoveries. When astronomers first tracked this motion using the cosmic microwave background as a reference frame, they found these colossal structures hurtling toward a point beyond the edge of our observable universe at speeds exceeding 2 million miles per hour, far too fast and coordinated to be explained by the gravity of anything we can see. The implications are staggering. On large scales, the universe's expansion should make everything drift apart evenly, like raisins in rising bread dough. Yet the dark flow suggests something out there, something beyond our cosmic horizon, is exerting an unimaginable gravitational pull. One theory points to the early universe's inflation. If space-time stretched unevenly during that explosive growth spurt, it might have left behind massive density variations, creating gravitational echoes that still tug at galaxies today. Think of it like finding footprints in the sand long after the tide has gone out, evidence of forces that vanished billions of years ago. But there's a catch: the scale of this flow exceeds even inflation's wildest predictions. That's where things get truly speculative. Some physicists suggest the dark flow could be evidence of other universes brushing against ours in the multiverse. Imagine a cosmic game of bumper cars where neighboring universes, each with their own physics and dimensions, occasionally nudge one another through higher dimensional space. These collisions would leave no direct trace we could see, but their gravitational wake might ripple through our universe, shepherding galaxies like leaves caught in a wind from another world. It's a breathtaking idea, but not without skeptics. Critics argue it might be a measurement artifact, or that our models of large-scale structure are missing key ingredients. The hunt for answers has driven some of astronomy's most ambitious surveys. The Planck satellite mapped the CMB with unprecedented precision, revealing subtle temperature shifts aligned with the flow. Hints that whatever's causing this motion leaves fingerprints in the universe's oldest light. Meanwhile, projects like the Dark Energy Survey trace the motion of thousands of galaxy clusters, searching for patterns that might reveal the flow's true source. Each new dataset tightens the mystery because the dark flow refuses to fit neatly into any existing cosmic framework. What makes this enigma so profound isn't just the science, it's the philosophical shift it demands. For centuries, we've assumed the observable universe was the entire playing field. But the dark flow whispers of something grander, a reality where our 14 billion light-year horizon is just a speck in a far vaster tapestry. Whether the culprit turns out to be primordial imbalances, other universes, or something beyond our current imagination, one truth remains: the cosmos isn't just expanding. It's being pulled, shaped by forces we can't yet see, reminding us that the greatest mysteries aren't always in front of us. Sometimes they're just beyond the edge of everything we know. Einstein's theory of general relativity paints gravity as the curvature of space-time, a smooth, geometric dance where planets and stars mold the cosmic fabric like weights on a trampoline. Quantum mechanics, on the other hand, describes the subatomic world as a frenetic, pixelated realm where particles pop in and out of existence, governed by probabilities rather than certainties. Both theories are spectacularly successful in their own domains, but when you try to combine them, to describe gravity at the scale of atoms or inside black holes, the equations explode into nonsense. This isn't just a technical hiccup. It's a screaming contradiction at the heart of modern physics, and solving it might require rewriting the rules of reality itself. Enter string theory, one of the most ambitious attempts to bridge this gap. Imagine if every particle in the universe weren't a point but a tiny, vibrating string, with different frequencies producing different masses and forces. In this framework, gravity emerges naturally from the harmony of these vibrations, weaving space-time and quantum fields into a single tapestry. The elegance is undeniable, but there's a catch. String theory requires at least 10 dimensions to work, 6 of which are curled up so tightly we'll likely never detect them. Worse, it predicts a near-infinite number of possible universes, making it notoriously difficult to test. Supporters argue it's the only game in town with the mathematical muscle to unify physics. Critics counter that without experimental proof, it's more philosophy than science. Then there's loop quantum gravity, the scrappy underdog of unification efforts. Instead of extra dimensions, it proposes spacetime itself is granular, a network of interwoven loops so tiny, 1,000,000 billion could fit in a single atom. In this view, black holes aren't bottomless pits but dense knots where space's fabric tangles into quantum foam. Unlike string theory's abstract elegance, loop quantum gravity sticks close to observable physics, but it struggles to explain how smooth spacetime emerges from such chaos. It's like trying to reconstruct a glass mirror from a pile of shattered fragments, possible in theory, but the math gets messy fast. The stakes couldn't be higher. Without quantum gravity, we can't understand the birth of the universe, the core of black holes, or whether time itself has a smallest possible unit. Some researchers are sidestepping theory altogether, hunting for experimental clues. Gravitational wave detectors listen for quantum jitters in spacetime. Particle colliders search for extra dimensions leaking energy. Even tabletop experiments with supercooled atoms probe whether gravity behaves differently at microscopic scales. What makes this puzzle so gripping isn't just the technical challenge, it's the philosophical whiplash. For a century, physics has thrived on dualities: wave and particle, space and time, matter and energy. But quantum gravity forces us to confront a deeper truth, that reality might not just be stranger than we imagine, but stranger than we can imagine. Whether the answer lies in strings, loops, or something beyond our current vocabulary, one thing's certain: the universe isn't just keeping secrets. It's daring us to think in a whole new language. If black holes are the universe's ultimate sinks, swallowing everything that crosses their event horizons, then white holes would be their mirror opposite cosmic fountains, gushing matter and energy into the cosmos with unstoppable force. This isn't just science fiction. The equations of general relativity actually permit such bizarre objects. mathematical doppelgangers where time runs backward compared to their dark twins. Picture a black hole in reverse. Instead of a point of no return, a white hole would have a point of no entry, hurling out radiation and particles so violently that nothing could ever fall in. The implications are mind-bending. Some theorists suggest white holes could be the other end of black holes' tunnels through space-time, where matter swallowed by a black hole re-emerges somewhere else, like a cosmic recycling plant. Others propose they might be remnant fireballs from the Big Bang itself, pockets of primordial energy that never fully expanded, lingering like embers in the cosmic background. The most radical idea, that our entire universe could have erupted from a white hole's cataclysmic outburst, making the Big Bang less of a singular event and more like a single bubble foaming up in an infinite sea of space-time. But here's the catch: no one's ever observed a white hole. If they exist, they'd be spectacularly rare or spectacularly short-lived. Simulations show that any white hole forming in our universe would likely collapse instantly under its own gravitational pull, morphing into a black hole before it could spew more than a flicker of energy. That hasn't stopped astronomers from searching. In 2006, a gamma-ray burst named GRB 060614 flared with such unusual intensity that some wondered if it might be a white hole's death rattle. The signal didn't repeat, leaving the mystery unsolved. What keeps this hypothesis alive isn't just math, it's the tantalizing gaps it might fill. For instance, fast radio bursts, those enigmatic cosmic flashes, could theoretically be white holes pinching off into non-existence, their final screams echoing across the cosmos. Even dark matter gets a possible tie-in. Some models suggest white holes could shed exotic particles as they evaporate, seeding the universe with invisible mass. The beauty of white holes lies in their audacity. They force us to confront questions we barely know how to ask. If time flows backward inside them, could they host entire inverted universes? Are they the universe's way of balancing its books, ensuring that what goes in must come out? Or are they mere mathematical phantoms, ghosts in the machinery of relativity that reality simply ignores? For now, they remain a glorious thought experiment, a reminder that the universe's imagination outstrips our own. And sometimes that's enough, to dream the impossible cosmic dream and let the equations guide us toward the unimaginable. The thin, rust-colored air of Mars holds a secret, one that arrives in whispers, lingers briefly, then vanishes without a trace. Since 2004, orbiters and rovers have detected sporadic bursts of methane gas in the Martian atmosphere, sometimes spiking to 10 times background levels before dissipating within weeks. On Earth, 95% of methane comes from living organisms, from microbes munching on organic matter to cows digesting grass. So when NASA Curiosity rover sniffed these plumes in Gale Crater, the implications were electrifying. Could Mars, barren and frigid on the surface, harbor subterranean life exhaling this telltale gas? Or are we seeing the ghostly hand of geology, ancient rocks reacting with water in ways we barely understand? What makes these methane spikes so tantalizing and frustrating is their unpredictability. Unlike Earth's steady methane output, Mars emissions come in erratic pulses. In June 2019, Curiosity recorded a reading of 21 parts per billion, the highest ever observed. Yet by the time the European Space Agency's Trace gas orbiter swung overhead to confirm, the methane had vanished without a trace. This game of cosmic hide and seek suggests the gas might be seeping from localized vents or underground reservoirs, escaping in brief bursts before ultraviolet radiation or chemical reactions destroy it. The question is, what's cracking open these temporary windows? One camp points to biology. Extremophile microbes thrive in Earth's most hostile environments, from acidic hot springs to Antarctic ice sheets. If similar organisms exist beneath Mars' permafrost, perhaps in briny aquifers where liquid water lingers, they could produce methane as a byproduct of metabolism. There's precedent. In 2015, researchers found methane-producing archaea in Canada's Arctic permafrost, surviving without oxygen at temperatures mimicking Martian conditions. If life took root on Mars billions of years ago, when lakes dotted its surface, these hardy survivors might have retreated underground, their gaseous signatures occasionally bubbling up through cracks. Yet geology offers equally compelling alternatives. Mars' crust is rich in olivine, a mineral that reacts with water to produce serpentine and methane in a process called serpentinization. Seasonal temperature changes or meteorite impacts might briefly unseal ancient fractures, allowing trapped methane to escape. Even more intriguing is the possibility of clathrates, ice like cages of water molecules trapping methane beneath the surface. These frozen reservoirs could destabilize sporadically, releasing bursts of gas like a carbonated can shaken by tectonic shivers. The answer may lie beneath our feet, literally. Future missions like NASA's Mars Life Explorer, set to drill 2 meters below the surface in the 2030s, aim to sample soil shielded from radiation where microbial life might persist. Meanwhile, the ESA's Rosalind Franklin rover will analyze organic molecules with unprecedented precision. Every new dataset brings us closer to solving this cosmic riddle, not just for Mars, but for every icy moon or exoplanet where methane flickers in the atmosphere. What makes this puzzle so captivating isn't just the hunt for life. It's the realization that Mars, long considered a static museum of rocks and dust, might still be geologically or biologically alive. Each methane whiff is a question written in a language we're only beginning to decipher, reminding us that the universe's most profound answers often come not with fanfare, but in fleeting, enigmatic whispers. And somewhere beneath that crimson soil, the truth waits, whether it's the first breath of an alien ecosystem or simply the sigh of a planet still stirring in its sleep. Venus hides its secrets behind a curtain of sulfuric acid clouds, a toxic shroud where temperatures roast metal and pressures crush submarines. That's why the astronomical world erupted in 2020 when researchers announced they detected phosphine gas wafting through this hellish atmosphere, a molecule that on Earth is almost exclusively produced by microbes thriving in oxygen-free environments like swamp mud or animal guts. For a brief, electrifying moment, it seemed we might have stumbled upon the first credible hint of life beyond our planet, floating improbably in the most hostile skies imaginable. The detection came from the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Array in Chile, spotting the telltale absorption line of phosphine at a concentration of 20 parts per billion, enough to rule out most known geological or atmospheric processes that could generate it. But Venus, ever the cosmic tease, wasn't about to surrender its mysteries so easily. Almost immediately, the scientific community split into fierce debate. Independent teams reanalyzing the data argued the signal might be sulfur dioxide masquerading as phosphine, or even an artifact of how the original team processed their observations. Follow-up studies using different instruments failed to confirm the detection, leaving the tantalizing possibility hanging in limbo. The controversy cut to the heart of a fundamental question. If phosphine is truly there, how could it persist in an environment where sulfuric acid should rip such molecules apart within minutes? The biological hypothesis dares us to imagine extremophiles unlike anything on Earth, microbes floating 50 kilometers above Venus' surface, where temperatures and pressures are almost hospitable, encased in protective droplets of sulfuric acid. These hypothetical organisms would need to metabolize differently than any known life, perhaps using metals or exotic chemistry to survive. It's not entirely far-fetched. Earth's acid-loving archaea prove life can thrive in punishing conditions. But Venus presents another puzzle. Without liquid water, how would biochemical processes even function? Some theorists propose concentrated sulfuric acid could serve as a solvent, though no known life uses it this way. Non-biological explanations are equally fascinating. Phosphine might form through unknown chemical reactions between Venus' volcanic gases and its mineral-rich surface, or be delivered by meteorites vaporizing in the atmosphere. Lightning could play a role, though calculations suggest it would produce far less phosphine than observed. There's even a speculative idea involving high-energy particles from space triggering exotic chemistry in the upper clouds. Each theory has holes, yet all underscore how little we understand about Venus' complex atmospheric dance. The stakes transcend academic debate. If phosphine does indicate life, it would shatter our Earth-centric assumptions about habitability. Venus clouds, once written off as sterile, might suddenly become the most intriguing astrobiological target in the solar system. Future missions like NASA, Da Vinci Plus and Veritas, along with ESA's Envision, aim to settle the question with precision instruments capable of distinguishing phosphine from lookalike molecules. These probes will also map the planet's mysterious dark patches, UV-absorbing regions some scientists speculate could be microbial blooms. What makes this mystery so compelling isn't just the possibility of life. It's the reminder that even our nearest planetary neighbor can upend expectations. Venus, long dismissed as a cautionary tale of runaway greenhouse effects, might yet harbor surprises in its swirling, acidic skies. Whether the phosphine signal proves to be microbes, exotic chemistry, or something even stranger, one thing is certain. The universe loves hiding its most astonishing secrets in the last places we think to look. And sometimes the most profound discoveries begin not with a shout, but with a single, disputed spectral line whispering from the clouds of a forgotten world. The Sun's surface simmers at a blistering 5,500 degrees Celsius, hot enough to vaporize steel in seconds. But step just a few thousand kilometers above that fiery boundary, into the wispy outer atmosphere known as the corona, and temperatures skyrocket to an unfathomable 1,000,000 degrees or more. It's as if you walked away from a campfire only to find the air around you suddenly 100 times hotter than the flames themselves. This cosmic oven, visible during solar eclipses as a pearly halo of plasma, has baffled physicists for nearly a century. How can the Sun's crown be so much hotter than the surface below? And what invisible furnace keeps it raging, even as it stretches millions of kilometers into the frigid void of space? One leading suspect is the Sun's tangled web of magnetic fields. Unlike Earth's relatively orderly magnetic field, the Sun's is a chaotic mess of loops and kinks, constantly twisting and snapping as the solar surface churns beneath them. These magnetic waves, rippling outward like plucked guitar strings, might carry enough energy to superheat the corona, a process called Alfvén wave heating. Picture shaking a blanket vigorously. The energy you put in creates waves that travel through the fabric. Now imagine those waves dumping their energy into the thin coronal gas, turning it into a seething plasma soup. Spacecraft like NASA's Parker Solar Probe, which flies daringly close to the Sun's atmosphere, have detected these magnetic ripples in action, their energy matching predictions. But here's the catch: Alfvén waves alone can't fully account for the corona's extreme heat. There's still a gap in the energy budget, like trying to boil an ocean with a teaspoon. That's where nanoflares come in, tiny explosions a billionth the size of solar flares, first proposed in the 1980s. Every second, thousands of these miniature bursts might pepper the corona, each one releasing energy equivalent to a 10-megaton hydrogen bomb. Unlike their larger cousins, nanoflares are too small and frequent for telescopes to spot individually, but their collective heat could solve the mystery. Recent observations from the Interface Region Imaging Spectrograph IRIS mission support this idea, revealing telltale superheated plasma that fits the nanoflare profile. Think of it like popcorn. You might not see each kernel pop, but the steady snap crackle in the pan tells you it's happening. Yet even nanoflares leave questions. If they're real, why do some regions of the corona stay scorching hot while others cool rapidly? And why does the heat dissipate so unevenly? The plot thickens when you consider the solar wind, the stream of charged particles constantly blowing off the sun. This wind accelerates to supersonic speeds as it leaves the corona, suggesting some hidden engine is at work. Some theorists argue that magnetic reconnection, where tangled field lines snap and realign, acts like a particle slingshot, hurling material outward while dumping heat into the corona. Others point to switchbacks, bizarre kinks in the solar wind's magnetic field first spotted by the Parker probe, which might shuffle energy like a cosmic card dealer. Solving this puzzle isn't just academic. The corona's behavior drives space weather with eruptions that can fry satellites, disrupt power grids, and endanger astronauts. Understanding its heat could help us predict these storms. Future missions like the European Space Agency's Solar Orbiter are mapping the sun's magnetic field in 3D, while advanced computer models simulate nanoflare cascades down to the quantum level. What makes the corona's heat so mesmerizing isn't just the science, it's the paradox. A flame that burns brightest far from its fuel, a furnace without fire, a mystery lingering in plain sight every time the moon briefly eclipses the sun. Whether the answer lies in magnetic waves, nanoflares, or something we haven't yet imagined, one truth remains: sometimes the most illuminating discoveries come from staring into the light and daring to ask why it shines the way it does. Every story has an ending, but the universe's final chapter is still being written, and the plot twists are stranger than anything we could invent. Right now, galaxies are racing away from each other at ever-increasing speeds, driven by an invisible force we call dark energy. But where is this cosmic sprint taking us? Will the universe keep stretching into an endless frozen darkness, collapse back into a fiery crunch, or tear itself apart atom by atom? The answer lies in a tug of war between gravity's relentless pull and dark energy's mysterious push, a battle where we don't even know all the players. Let's start with the leading theory. If dark energy behaves like Einstein's cosmological constant, a steady, unchanging force woven into spacetime itself, then the universe is headed for what cosmologists call the Big Freeze. Galaxies will accelerate until they vanish over the cosmic horizon, their light stretched into undetectable infrared whispers. Star formation will sputter out as gas clouds grow too diffuse to collapse. Black holes will evaporate via Hawking radiation, leaving behind a sea of drifting particles approaching absolute zero. It's a slow, quiet fade to black, a universe that doesn't so much end as exhale. But dark energy might not play by those rules. What if it strengthens over time? In this nightmare scenario, dubbed the Big Rip, dark energy's push grows so dominant that it overwhelms every binding force in nature. First, galaxy clusters would tear apart as the space between them expands faster than light can bridge the gap. Then, individual galaxies would unravel. Stars would be ripped from their orbits, planets would disintegrate as the very fabric of spacetime stretches beyond atomic cohesion. In the final microseconds, even atomic nuclei and quarks would be shredded, an apocalyptic finale where the universe literally dissolves into nothingness. Then there's the cosmic boomerang possibility, the Big Crunch. If dark energy weakens or reverses, gravity could regain the upper hand, dragging everything back together in a mirror image of the Big Bang. Galaxies would blue shift as they hurtle toward each other, the cosmic microwave background warming until it glows like the surface of a star. The final moments would see all matter compressed into a singularity, a fiery rebirth that might spawn another universe in an endless cycle of expansion and collapse. The wild card: we still don't know what dark energy is. Is it vacuum energy, the hum of quantum fields underlying empty space? a fifth fundamental force that alters its strength over cosmic time. Or something beyond our current physics, a sign that general relativity breaks down on universal scales. Each possibility points to a different destiny. Experiments like the Dark Energy Survey and the upcoming Euclid telescope are mapping billions of galaxies to trace dark energy's influence through cosmic history. Even subtle changes in its behavior could tilt the scales between freeze, rip, or crunch. Here's the beautiful, terrifying truth: our universe's fate isn't just some abstract equation. It's etched into the redshift of every distant supernova, the clustering of galaxies, the way light bends as it crosses the cosmos. And as we peel back those layers, we're not just solving a puzzle, we're reading our own ultimate story, written in the language of dark energy's inscrutable hand. The grandest question of all isn't just where the universe is going, it's whether we'll live long enough as a species to understand the answer. From unexplained signals racing across the cosmos to galaxies that spin the wrong way, these 27 cosmic puzzles aren't just gaps in our knowledge, they're invitations. Every time we think we've mapped the heavens, the universe tosses us another riddle, as if to say, you're just getting started. Take Tabby's star flickering like a faulty light bulb in the void, or the Great Attractor pulling thousands of galaxies toward some unseen finish line. These aren't just curiosities, they're the loose threads at the edge of our understanding, waiting for someone, maybe you, to tug on them and see what unravels. Think about how far we've come. A century ago, we didn't know galaxies existed beyond the Milky Way. Today, we're decoding the afterglow of the Big Bang and debating the nature of dark matter. Yet for every mystery solved, a dozen more emerge, each more bewildering than the last. That's the thrill of exploration. The more we learn, the more we realize how much we don't know. The wow signal, those fleeting 72 seconds of radio noise, taught us to listen more carefully. The Kuiper cliff, that sudden drop-off at the edge of our solar system, forced us to question what else might be hiding in the dark. These puzzles aren't roadblocks, they're signposts pointing toward discoveries we can't even imagine yet. And let's be honest, some of these enigmas might never be solved in our lifetimes. The true nature of dark energy, the possibility of parallel universes, the question of whether we're alone, these could remain open for centuries, but that's the beauty of science. It's not just about answers, it's about the chase. Every telescope pointed at the sky, every algorithm sifting through data, every kid staring up at the stars and wondering what if, is part of the same grand project. We're all detectives in this cosmic mystery novel, turning pages together. So here's your challenge. The next time you step outside on a clear night, pick one of these puzzles and let it linger in your mind. Maybe it's the eerie silence of the Fermi Paradox, or the way Oumuamua defied every rule in the book. Whatever sparks your curiosity, follow it. Share your thoughts in the comments, debate with fellow explorers, and keep asking questions. Because the universe isn't just hiding its secrets, it's waiting for us to find them. And who knows, the next great revelation might come from you. If you've enjoyed this journey to the edge of the known, don't forget to subscribe. There are always more mysteries waiting just